Today is my first day at school. I hope that I don't break the rules. Headmaster's my friend, he's clean round the bend. Today is my first day at school. We went on the playground at break. We tied Eric Ford to a stake. And Mary Jane Vickers, she showed me her knickers. Today is my first day at school.
Hello, everybody. That is a song by a kids' TV show in England called Basil Brush that I remember watching when I was probably about 3 or 4 years old and still lived in London, England. And I just thought that was a cool song to have a little start to the video with. I like that little start thing so that you guys have time to press play and get settled in and realize what you have and what you don't have and what you need. And let me just pull my green screen a little closer. I'm seeing a little fuzz here, and then we'll let that focus in, and live videos type thing. So gotta let that find me. There I am. Oh, good. So this week I want to talk about Bernoulli variables. And a Bernoulli variable, not very well discussed in our textbook, even though it's discussed in many other stats textbooks. And a Bernoulli variable is effectively a variable that takes on one of two choices. And we normally label those choices success, which is a 1, or fail, which is a 0. Okay? So we're going to go to the board. And here we are. And so a Bernoulli variable is one in which, and I'll do this from a tree perspective, we have a success and we have a fail. Now, a fail could also be called a success complement in some books, but here we're looking at it as a fail. So that's good enough for us just to call it a fail. Now, when we're looking at a Bernoulli variable, we assign the probability of a success P, and that means by necessity, a probability of failure is 1 minus P. Now, I want to make sure you realize that the question doesn't have to be set up as a Bernoulli variable. I could easily have a situation where maybe I have 1, 2, 3, 4, and 5. And let's assume that these have probabilities 1 over 5, 1 over 5, 1 over 5, 1 over 5, and 1 over 5. And then from here, I'm going to say that a success is if I get an even number. So we'll call that a success. And a failure is if I get an odd number or not an even number. So we'll call that a failure. And if we look at the success, 2 and 4 are successes. So our P would be 2 out of 5. And our fail, 1 over P, is equal to 3 out of 5, both by counting and by mathematics. So this is a Bernoulli situation. And when we perform this type of math with Bernoulli variables, what we expect is that the Bernoulli variable, we just keep repeating the experiment. So here we have a success, and here we have a failure. Here we have a success, and here we have a failure. And we have this assumption that they are independent trials. We actually call them IID, identically independent trials. We change nothing except the fact that the outcome is random, so we don't know if we'll get success or fail. And so that means this is still P, and this is still 1 minus P, and this is still P, and this is still 1 minus P. Our examples of drawing the numbers 1, 2, 3 out in video 1 this week could be Bernoulli if we designated a success and a failure in that experiment. And of course, we can keep going if we wanted to, and keep building off more and more and more. So here we have another success, another failure, another success, another failure, another success and failure, and another success and failure. Now, P1 minus P, P1 minus P, P1 minus P, p and 1 minus p. Now, when we're looking at Bernoulli variables, a lot of the times the question we have to ask ourselves is, what is our goal? Okay, what is our goal? What is it that we're interested in studying with this Bernoulli variable? And we're going to look at 3 cases. So case number one is a case we are going to call the geometric distribution. And in the geometric distribution, it's how many times we run the experiment to get, let me fix that word get. I know I'm saying it and you guys don't really need me to write it, but just like class, we write it on the board for those that need it there. How many times we run the experiment to get our first success. And this is kind of interesting if we come up and look at our chart, because this would mean, for example, that this part of my table would be done because the first one there was a success. And then this part of the table would be done because the second one is a success. So we have this idea of an experiment that keeps going. And of course, this keeping going would have a success. Oh, let me change that to black. Let me just maybe move this out of the way a tiny bit and move this as far out of the way as I can get it there safely. So here we have a success or a fail, and there's a success or a fail, and there's a success or a fail, and there's a success or a fail. And this theoretically goes on forever and ever and ever. This question of asking how many times do we run the experiment to get our first success is called geometric. Now, there are some assumptions. Our assumptions are this IID is that every time you run the trial, you have the same chance of success, the same chance of failure. It never changes. Those two don't have to be equal, but it could be 75% chance of success and a 25% chance of fail. That will be the same every time. And the success or fail on the first attempt doesn't influence the probability of success or fail on the second attempt. It's actually the same rule, just stated differently. So this just basically tells us that because this is P, this is P, this is P, this would be P, this would be P, this would be P, this would be P. And because these are 1 minus P's, that one's already there. But here, 1 minus P, 1 minus P, 1 minus P, 1 minus P, and so forth and so forth and so forth. So we have this idea of a geometric distribution. Try to think for a second of a situation that you would think would fall under the category of geometric, right? So in my personal life, I struggle with weight loss. I think many people in today's environment here in Canada do. And there is a weight loss program I partake in. And I've partaken in it a few times. You know, you go on, you go off, you go on, you go off. And maybe what I'm going to measure is, do I manage to maintain my weight loss after leaving the program? And if I assume, and I have to assume this because I'm not a god, I don't have omnipotent knowledge. If I assume that each question either has the same probability of yes or no, then that's a geometric distribution. And I could look at working out some probabilities. Now, how would we do that? Well, let me just clear my box there. For geometric, first of all, the probability of a success is equal to P, and the probability of a failure is equal to 1 minus P. And our discrete random variable, xi, what we said, it's the number of trials to get the first success. So this means xi could be, well, I could get a success on my first trial. So the lowest number xi could be is 1. I cannot get a success if I don't run the experiment. But it could be my second trial, my third trial, my fourth trial. I can't do 4.5 trials. My fifth trial. And theoretically, it could go all the way to infinity. And so this is something we haven't seen before. Before, all of our discrete random variables had a small set of numbers, but the geometric distribution has an infinite size of numbers. And this means we definitely don't want to work out infinite probabilities, and so we hence use formulas and things like this. Now, what's the probability of each of these xi's? Well, for one xi, it's just success, which is p. For 2, it had to be fail, then success, so 1 minus p times p. For 3, it had to be 2 fails, and on the tree would have been 1 minus p, 1 minus p, and p. And so it turns out that the formula for the geometric distribution is always p onto 1 minus p to the x minus 1, where x equals 1, 2, 3, and to infinity. And math does prove that the total is 1. Math can very easily prove that the total of this entire sum of infinite numbers happens to be 1, which is one of our basic rules of probability. So let's go in and look at this. Let's do an example. So let's, I have a coin which does heads with probability 0.1 and tails with probability 0.9. And I want to say how many flips to get the first head. So because I'm asking how many flips to get the first head, a success is equal to a head, and the probability of success is equal to 0.1, which we're going to call p. So this tells me that the probability of any xi is equal to p under 1 minus p to the x minus 1, or xi minus 1, which is 0.1. 1 minus 0.1 is that probability of failure, xi minus 1. Let me just move that over a bit. So if I wanted, for example, what is the probability of 4 flips to get the first head? What's the probability of exactly, and this is exactly 4 flips to get the first head, p of 4 is equal to 0.1 times 0.9 to the 4 minus 1 is 3. And let me just open my Windows calculator again. 0.9 times 0.9 times 0.9 times 0.1 is 0.0729. I know you can't see the calculator, but that's fine. You have a calculator in front of you. So it turns out that 7.29% chance of getting a heads in 4 flips. Now I'm actually going to open Excel. Excel is a piece of software we haven't used a whole lot. Let me just get it open here, see which monitor it's opening on for me. Monitor 3, bring it up here to monitor 2, switch to mini tab, and go into an empty sheet. So of course Excel is kind of like our mini tab, except it does math. And so one of the nice things in Excel is I could work out x and p of x, right? I'm just going to center these, and I'm going to highlight this with an underline, and I'm going to make my columns a little bit bigger. And I have to type in what I think my x values are. So 1, 2, 3, 4 is where we've been at. And then I can use a nice piece of Excel work. I know that P is 0.1, so I'm going to go 0.1 times, and let me actually zoom in here. Let me make this a little bigger for you guys to see. That'll be better. So actually, while I'm here, I might as well teach good Excel habits. I'm going to insert a line here, and I'm going to write a line P equals, and put 0.1 here. So here, I'm going to go, the probability formula is P multiplied by 1 minus P, and I'm just referencing that, to the power, and then I bracket x minus 1. And this first one should be pretty easy. The chance of getting a success on the first time is 0.1. Now, in Excel, there is a thing called locking a cell. When I bring this formula down, I want you to see that this formula uses B5. B5 is the 2, that's right. But it moved down from C1 to C2. So I have to go back up here, and I have to lock in a formula. Hitting F4 on a cell locks in that formula, okay? Now, we don't use Excel as part of this course, but it's a good tool to have. So now that I lock in that value of P, I can literally just grab this little dot called the handlebar and drag it down. And you're going to see under our P of 4 that it's 0.729. And I could take this and drag it a lot further. Okay, and now let's scroll up. And my formula has effectively calculated it for all these values. This is a beautiful feature about using Excel. So I'm going to show 4 decimal places. I think for this course, 4 decimal places is usually good enough for most of the work that we're going to do. And so whenever you're not sure of how many decimal places to use 4. Also use rounding. Excel does it automatically. Rounding says that if the 5th decimal place is a 0, 1, 2, 3, or 4, you round down. But if the 5th decimal place is a 5, 6, 7, 8, or 9, you round up. Okay? So here we see our probabilities, and you can see that eventually they get quite low. So look at this one. This is 0. So this line right here says the probability that we don't get our first heads until flip 74 is 0. Now we have to remember that it's not actually 0. It is very possible that we flip this coin 73 times, getting tails, 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 and then get a heads on 74. That is a possibility. However, it is very improbable. It is a low probability, and I could extend this one's decimal place to show that it's not actually 0. Okay, but we'll report that. What you need to do when you're writing stats up is you have to remember to never write it's equal to 0. And you would always want to write it's approximately equal to 0 in this situation. Okay? Same as in Excel, I can highlight these numbers. And when I do so, I'm going to just have to move me out of the way for a second. Ready? There we go. All right. Down here in this corner, you'll see the sum of what I have highlighted. Okay? And the sum of what I have highlighted right here is 1. That's because the total probability is approximately 1. All right. Let me move me back. There we go. Now, the other thing that we have looked at in this course, my line is in the way, so I can't see it. Cumulative. That's spelled wrong. Cumulative. There we go. So cumulative probabilities. So cumulative probabilities is also something very important in our world of probability. So cumulative probability is actually just the probability of being less than or equal to. Remember, this is less than or equal to. So here, whereas 9% is the probability of getting a 2, a first heads is on our second flip, it turns out that 19% is the probability of getting our first heads on our second flip or earlier. And we can run this down and add this formula to all of our values, and we see that it is definitely there. So 4, whereas we had a 7.29% chance of getting a heads on our fourth flip, it turns out we have a 34.39% chance of getting a heads before our fourth flip or earlier. And by the way, we can change these to percentages in Excel by hitting this percent button and then extending the number of decimal places back up. And you can actually report these as percentages. So what's the chance? If a heads shows up 1 in every 10 flips, what's the chance I get my first heads in my 10th flip or earlier? 63.13%. Because these distributions occur for so many real life situations, we actually have tables that we can find for these tables. Now, I posted into D2L my version of a table for this, and usually our version of the table only includes the cumulative column. We would actually not have this column sitting there. We would just have the cumulative. And so if this case, if I ask what's the probability x is equal to 7, well, what do I know? I know the probability x is less than or equal to 7 is, and I'm just going to reference here, 52.17%. I know the probability x is less than or equal to 6. That is 46.8%. So therefore, the probability of x equals 7 is the probability that x equals 7 or less minus the probability x equals 6 or less. So I can calculate individual ranges or individual values based on these tables. Okay, we'll be seeing more of these tables, so I think that's enough of an intro for that table there. We're also hitting the 22-minute mark. And I don't like videos that go that long because I know that you have lives. You might have kids running around, husbands running around, kids running around, husbands being annoying, wives being annoying. Who knows, right? So let me just get that to focus in on me. So we'll end that video there, and that's geometric. When we come back, we have 2 more cases to look at, probably 2 different videos for discrete random variable special situations. Toodles!
Think that I'll just play it cool. Can't do my sums right, and my nose needs a wipe. Today is my first day at school.